And the nice thing about going right after Joanna is I get to reuse the computer, so less transition time for everybody. Yeah, I wanted to start out by thanking everyone in the room today for coming out and watching our presentations. And I wanted to start by reiterating something that was mentioned earlier, but that we are speaking on the traditional, ancestral, and contemporary homelands of the Dakota people. And in addition, that the project I'm presenting on today, we hypothesized and practiced on the traditional homeland of the Kalapuya Ili in what is now called Oregon's Willamette Valley, who are dispossessed of their homeland by the US government and whose descendants continue to make invaluable contributions to the University of Oregon and to our land as a whole. With that said, my name is Lucy Roberts, and I have been working in the InfoGraphics lab for 3 years. I completely forgot I said to say that, so I can repeat it now. And for a lot of that time, I've been working on a question that was posed originally to Joanna by two economists at the University of Oregon, Dr. Wen-Fong Wong and Dean of the School of Business, Bruce Blonigan. And they were interested in how the adoption of new maritime technology impacted global oceanic transit. So their challenge to us, and we did choose to accept it, was to engineer a method which we could use to compare maritime transit between a list of global trade ports amidst two different technological paradigms, the sailboat and the steam engine. And originally, when they approached us with this question, they brought us Luigi Pascali's 2017 paper in the American Economic Review, where Pascali used a weighted wind raster to compute the most efficient travel times using sail and steam using Dijkstra's algorithm. Perfect, right? Except that the methodology section was pretty sparse and the tools were not publicly available. After we did not hear back from an email we sent out, we turned to Gianmarco Alberti's more recent 2020 paper, Transit, a GIS toolbox for estimating the duration of ancient sail-powered navigation, in which Alberti used a least cost surface raster analysis, which we will totally touch on later, and applied it to a localized region in the Mediterranean. His toolbox was available upon request, and it's with deep gratitude for his contributions to the fields that I now stand before you presenting on how we expanded on his methodology to create a toolbox which we plan to call Transit Global. But before we get into the nitpicky details of that, I wanted to kind of step back and give an overview of what that process looked like. So, we were using a least cost surface analysis. And technically, a least cost surface analysis is a geospatial analysis that identifies the cells which together form the path that uses the least cumulative resources to reach a specific destination from an origin across a raster surface. I'm out of breath, you guys. That's a lot of words, and this is a cartography conference. So let's look at some maps and break that down a little bit. The process begins with some raster, which indicates the challenge of moving between various cells. If you were to perform this analysis on, say, land, you could use a weighted DEM to show the cost of traveling across terrain, for example. But since we were working in maritime transit, we used wind speed and wind direction. For each of the cities in our list, and we had over 250 cities, we then generate an accumulated cost raster, which shows the time it would take to get from one city around the globe. Here, I have a stylized version of an accumulated cost raster that goes from La Plata, Argentina, where green indicates the lowest cost, or the quickest amount of travel, quickest travel time, and red indicates the highest cost, or the least travel time. And finally, the last step is to create a least cost path, or the route that uses the fewest cumulative resources to get from that origin to another destination point. So the example here is from La Plata, Argentina to Bangkok, Thailand. And with that said, this is the model that Alberti created in order to start working on that process. And I would really love to just kind of pause this whole presentation here and point out that this is the wildest ride of an acronym you will ever go on. So all told, Alberti's transit model stands for Toolbox for Ancient Sailing Time Estimation. And no, in the final published paper, there's no final T in transit. But the input parameters, understanding the input parameters are key in order to validate the historical accuracy of this process. So here are a few of the key model parameters I wanted to touch on. First, wind speed was a data layer provided to us from the World Ocean Circulation Experiment's global data, and it was provided to us on a CD-ROM from our research partner, Dr. Wenfang. Then wind direction was a raster from pre-processed WOS data. It's the product of the tangent of the zonal wind speed layer divided by the meridional wind speed layer, the details of which you don't need to know unless you want to look back at this slide and recreate this later. The max scale value is the maximum speed a ship can travel, regardless of wind speed or wind direction. So essentially, even if you have a sail ship that's going full steam ahead, super powered, like winds right behind the sails, this is the maximum limit to the capabilities of that sail ship. The horizontal factor is a multiplier cost for travel in between cells. It also reflects the challenge of turning the ship, so it indicates the challenge of rotation. And then the source location, important to note in Albertis model, is a single point, which is the origin for each of these models. So the first part of the transit model accumulates that cost raster I touched on earlier from a single city and outputs a backlink layer. This then feeds into the second part of his model, which processes and outputs contours for the given city. And while this initial model is pretty powerful, I want to touch on some of the key limitations of it for our workflow. First, it only works for a single source location at a time, which means that we were not able to use it on, say, a global data set of 250 cities. Additionally, while it does data pre-processing and outputs an accumulated cost raster, it does not generate the final least cost path. Albertis leaves that up to the individual researcher. So in the example I gave earlier, this would output the accumulated cost raster from La Plata, but would not generate the route from La Plata to Bangkok. And so to address these limitations and to solve other challenges, this is our adaptation of Albertis' original model, which we are tentatively entitling Transit Global. We changed the layout a little, but the basic building blocks that I touched on earlier are still there. Additionally, we added an iterator to the beginning of the model so that we could loop through our entire city list. And naturally, because of the scale and the amount of data we wanted to process, we also wanted to automate the process of generating the least cost path. And that's what you'll see in this section here. In this portion, we needed to nest for loops so that each origin could go to each other destination, which meant that we had to add 2 additional submodels into the process. The first calculates the routes, or calls the route from the origins to the destinations. And the second submodel generates the paths for each origin and destination pair. Finally, it outputs a merged shapefile, indicating the destination for each origin city, the time and distance it would take to travel. However, attempting this on a global scale introduced a new problem, which we tentatively titled the Atlantic-Pacific Conundrum, specifically for this presentation. Previously, Albertis had applied his workflow to the Mediterranean, so he didn't have to worry about wrapping around the edges of the Earth. The previous maps I showed were stylized, but this is more what the underlying data looks like. It's a Boolean raster where 1 indicates traversable ocean and a 0 indicates land. So, using this model, the modeled least cost from San Francisco to Singapore would look something like this. However, as very keen-eyed cartographers, we intuitively understand that the least cost path from San Francisco to Singapore would probably look something like this, but it gets cut off by the edges of the Earth. This is an annoying problem. I didn't want to work on it, and so that's why I'm standing before you today, having accepted a blue ribbon for my work. You know, like my entire goal coming into this was to make the 9 a.m. software programming and tools room like giggle, and so I would like to call this a successful presentation. Thank you. No, in actuality, we realized that we would have to solve for both Atlantic and Pacific transit. And so we needed to modify the workflow in order to account for both scenarios. First, we ran the data set on two projections. The first one, which I showed before, is an equidistant cylindrical projection centered at 0 degrees latitude, or through Greenwich, England. Then we run the model again on a Pacific-centered projection, also equidistant cylindrical, where the central meridian is at 180 degrees of latitude. Now, this is a way for us to create a true least cost path for each of our origin-destination pairs, but it introduces a new problem. For each of these origin-destination pairs, how can we tell which one is the true least cost path? So naturally, if you're going to try and address this kind of problem, you want to iterate through and compare all of the values and see which one's the shortest one and output the results. But this was further complicated by a couple of problems. Number one, the Atlantic-Pacific conundrum again. As you can see here, when I was talking about the Boolean raster earlier, you can't go past the edges of the raster. So when we move the central meridian to 180 degrees, it cuts off some of these cities that are in the Mediterranean and in Northern Europe. That means that we needed to support two different city lists, one for an Atlantic projection and one for a Pacific projection. And we then needed to compare against them, but add additional functionality into our script so that we could skip past a origin-destination pair that didn't have a comparable value in a different data set. So finally, we assembled a script that could compare and output data from hundreds of different shapefiles, putting them into an intermediary folder so that we could point to multiple different directories, skip over entries without a point of comparison, and update single entries if needed, so that if, for example, we only wanted to rerun our Atlantic data set, we wouldn't have to then rerun the entire workflow. We could just update that singular entry. So in addition to modifying the original model for our use case, we added new model variations for extra functionality. First, our original mandate was to compare the steamship and sailing ship. And as Blue Ribbon Award-winning scientists, the only challenge was we really only wanted to change one variable in order to compare between those two. So we knew we were going to have to apply a similar algorithm to our steamship. However, since the main advantage of the steamship was that it no longer relied on a renewable energy source to power it, we didn't have to account for the cost of wind speed and wind direction. Instead, we were just using a Boolean raster unweighted by wind in order to calculate the steamship's travel. The resulting model is pictured right here below, the details of which you cannot see because it's tiny. But the key thing is that it's much more sparse in the middle than the original model I showed you, and that's because it does not require nearly the same amount of raster input or data preprocessing. And I want to pause here to address one kind of tangential question that came to us while we were looking at this specific question. And it's something that I just find really interesting, because steam engines, once they were invented, needed to stop periodically at coaling stations. So the trade-off between not relying on wind was that you were then reliant on these other geopolitical factors. But this posed a huge challenge to us as data modelers, because as the technology developed and as the steam engine no longer required coaling as frequently, as geopolitics changed and the coaling stations changed, it's hard for us to understand how to compile a data set that would then reflect those shifting geopolitical and technological issues. And so we came to the conclusion that our job was to model a global data set. And if we then were able to find historic example of, say, travel from Argentina to Thailand with stops at specific coaling stations, we could break up that travel into multiple different segments and compare our total cost. Our goal was not to try and model it like each little variation in the coaling station stops, but rather to get a holistic view of how that travel would have gone from each of our origins to each of our destinations. And it's these kind of intricacies that are hard to approach and led to us having many heated discussions in our lab room, but that I find the most interesting when we're addressing problems like this, and I wanted to briefly touch on that. In addition to modifying the model itself, we developed and formalized workflows for modifying data inputs to compare many different variables. First, we started running the sailing data on 2 different data sets, one in June and the other in December, to account for seasonal variation. Additionally, the data are run using a raster mask in the ocean, and that allows for us to close and open canals when historically appropriate. This is especially important for the steam engine because the steam engine was gaining in popularity as the Suez Canal was opening. So to kind of back up and pause here, our model follows a queen movement paradigm, which means that the ship can move from one raster cell to any adjacent raster cell, whether that's horizontal, vertical, or diagonal. This allows for us to travel in any direction as long as it's adjacent to the starting cell. What it also means is that in order to just open up a canal, all we have to do is add a single raster cell. So here we're zoomed in on Latin America, and this is what it would take for us to open the Panama Canal, according to our model, is the addition of a raster cell through this area. This is also important as we have multiple different undergrads then combing through the raster, trying to find any places where we allow for travel that shouldn't allow for travel, or that we're closed to travel and should be open according to that historic accuracy. One challenge from introducing all these modifications is that it creates an incredible amount of variation in the number of variable configurations that we have. So this is an example run table for a given attempt to iterate through all of the data. First, you have to run through the sailing and the steam engine models using different weather patterns and whether or not the canals are open. But then you have to do it for multiple different speeds, and those speeds depend on whether you're using the sailing model or the steam engine model. And for each of those iterations, we have to have an Atlantic data set and a Pacific data set, which leads me into the additional challenges we faced throughout the development process, the biggest of which is runtime. Because we have an O-squared runtime factor, which means that for every city we add, it increases the runtime of our model exponentially. So since we have 253 cities, the number of total origin destination pairs we have is 253 squared, or over 64,000 origin destinations generated for each run of the model. And to reiterate, we have over 16 runs of the model in order to be complete. We're currently migrating the tool into ArcPro before working towards publication, and it is about 10 times slower to work in ArcPro. So we are currently playing with things like parallel processing factors, making some outputs optional, and attempting to write intermediary files to memory instead of explicitly writing them. However, if anyone has any additional ideas on ways to speed up this model in Pro, we would absolutely be open to feedback there. And finally, one issue with this was model validation, because we were checking against previous study data that didn't necessarily operate on the same scale that we did. And as I touched on briefly before, we didn't always have the historic records to be able to validate completely. Moving forward, our research partners are working towards publication on a series of analyses of the data that we're creating, and we are also looking to publish our model so that other people can continue to develop on it as well. If you have any additional questions, this is my contact information as well as Joanna's again, and we'd like to thank the NSF for funding this, as well as for my travel, NACIS, the UO Center for Undergraduate Research, and the UO Geography Department for letting me be here today. Thank you.